Joining me now are members of Project Shearwater team. You guys want to introduce yourselves?
I'm John Dean.
I'm Ricardo Mirandas.
Okay, and you guys are engineering students here at Notre Dame. What kind of engineering?
Aerospace.
Also aerospace.
Aerospace. Well, I guess that makes sense. Oh, the best. Here we go. We have an engineering competition right now. So you built this from scratch.
Yes.
Is that right? Okay, and what do you call this airplane?
Well, we call it the Shearwater, which is the name of the project, because of an ocean-going bird that has really good geolocation. This thing is supposed to fly itself, be autonomous. So we found a bird that we thought had a cool-sounding name, and we said, well, it works, right?
All right, so it took you how long to build this?
So we've been working with it since August of last year, so probably more than a year. From the design to construction to building to everything, it's taking a little more than a year for sure.
And what kind of payload does it carry?
Well, that's one of the cool things about the design is that actually it can carry any number of payloads from scientific apparatus and sensors to emergency medication that can be airdropped to hard-to-reach places, up to about 30 pounds even.
So this is like a drone on steroids.
You could say that, yeah, sure, yeah. That's one way of looking at it, yeah.
All right, so walk us through the process of putting this together.
So the assembly of the aircraft right now is only we have the fuselage of the airplane, and then we have both wings that we can separate so we can transport it. Little facts about the airplane: it's 13 feet and a half in wingspan, so this way, and there's 10 and a half feet this way. It weighs about 55 pounds. It has an 8.5 horsepower engine. It's probably going to fly like 60 to 70 miles an hour. And we can carry the 20-pound payloads, maybe even more. When we do more testing, we're going to find out.
So has this actually been airborne?
Wednesday, it will.
Oh, Wednesday is coming up. Oh, wow. That's amazing. And your confidence level and the fact that it will get off the ground?
100%.
Absolutely, 100%.
Yeah? Okay, well, you've heard that here. All right, so further commercial implications for this are?
Well, again, like I mentioned, there are all kinds of things that you can put inside this airplane. The purpose of it is to give companies the ability to make their product airborne. So if you have a camera that you want to put up, a sensor, an early warning system, a radar, whatever you want to, whatever you can fit inside it, if you put it at the right spot, it'll fly.
And walk us through how you put it together. I mean, okay, you're starting. I want to build an airplane. How does one do this? Where does the engine come from? Where do the wings come from?
Well, we started with the payload. Right? That was what sizes most of the airplane is how heavy the payload is going to be, what it needs to be able to carry. And from there, we start to design the wing, and that airfoil selection was interesting.
So all the mathematics behind it, it basically, once again, when you get the payload, you got to decide how acrobatic you want to fly, what different speeds you want to fly. Since we're just trying to fly an airplane, and obviously we're only senior aerospace engineers, as you can see, it's a very conventional airplane. We weren't going to design something that was going to complicate our lives, and we're not going to be able to finish in a year, because again, this is a school project, so we got to finish it to get a grade. So after we designed basically the wing to be able to carry 20 pounds and the structure, so we estimated that we were going to need about 40 pounds of structure. You can design the airfoil, then the fuselage. Then once you have your weight, you can select how much thrust you need of an engine. And there's commercially available engines nowadays that you could buy, especially because of the big RC hobby that exists out there. And that's when we bought the engine, and that's when we started to design our control surfaces. And after that is just figuring out a way to build it. And then after you design the shape of it, you got to first design, there's more than 600 pieces, individual parts in this airplane that we had to design individually in order to assemble it, right? Because we built this out of wood, so every single part had to be manufactured.
So this is wood?
This is all plywood.
It's all plywood. Mm-hmm. How heavy?
So in wood, there's about 40 pounds of structure, and it's a 6-pound engine. So in gas, there's going to be 6 pounds too, because it's a gallon of fuel. And there's going to be a bunch of other electronics to be able to control everything. So it ends up being around 55 pounds with 20 pounds of payload, 75 pounds.
Okay, so where is the experimentation, the first liftoff, going to take place?
Well, it'll actually take place about an hour or so south of campus at a place in Winamac, Indiana. It's the only place where we can actually legally fly it.
And why is that?
Well, the FAA has lots of regulations on aircraft, especially small unmanned aerial systems, as they're called. And this actually exists outside of those regulations. So we have to work with the Academy of Model Aeronautics, as well as the FAA, to make sure that we have all of the necessary paperwork in order to get this thing in the air.
Well, this is amazing. you have some helpers, I understand. Do you want to introduce them to me? These are also engineering students.
Yes, absolutely. So on our left, we have Jack Brooks, and then further to the right, we have Michael Boucher, and then just off camera, we have Wei Cao, who's here as well. So.
All right, well, best of luck to your entire team. I hope to heck that it stays airborne.
Me too.
How long are you expecting it to stay airborne?
Well, ideally, it'll stay about an hour or so, but for our test flights, we're going to limit those to about 15 minutes.
All right, good luck. Get a priest to bless you, okay? And thanks for bringing the Shearwater to Notre Dame Day.